So A here, would you classify it according to part one?
Is it one-to-one?
It's not one-to-one, no. In other words, it's not going to, for that reason, it's not going to have an inverse.
Because I can't remember how to do this.
So that's fine. Let's look at these graphs a bit more carefully. And yes, the other question they're asking about it, we'll probably end up mentioning anyway, which is whether they are a function or not.
Yeah.
So when is a relation between x and y coordinates called a function? It's
when is it? Actually, I don't know.
No, fine. Okay. I mean, are you used to thinking of x values as inputs to a function and y values as outputs from the function? I mean, you remember in primary school, they used to they say, here's a number machine. You know, if we put a number in here, what comes out the other end?
Yeah.
Depending on what was going on inside, or maybe it was one thing and then another, which is composition of functions.
Okay.
You know, this is kind of what we're looking at. Yes, on an XY graph, we generally are thinking of putting X in here and spewing out Y as an output. That's how to think of an XY graph in general, with that convention. X is horizontal, Y, the vertical is on the other. So for a particular input here, how many outputs are there?
There will be 0 for that.
Well, for this input, I mean, maybe it was 2 on the x-axis, we don't know.
Yeah.
But what it's telling us is that there is
an
output here of whatever that is, 3 or something, or whatever.
Yeah.
No point in putting numbers in there, really, with no idea. But the point is, this input has that output, but it also has another output.
Yeah.
The direct.
So it's one to many, then. Does he get?
Yes, that's right. I suppose we don't bother with many to many, which I'm inclined to wonder about. That's not one of their options, is it? One to one, many to one, or one to many. No, we don't worry. There's an asymmetry there. I suppose, in a sense, we could say that insist that this was many to many, but things would get complicated in terms of the. This is another important diagram they may use in your book. If you think of the x values here heading or mapping to corresponding y values over here.
Yeah.
Obviously, the x values were horizontal, but now we're maybe flipping or rotating them or something and representing them vertically. But we can see that, yes, this x value of 2 is leading to maybe both -1 and 1. So it's one to many in that literal sense, that we're going from one input to many outputs.
Is that if you have a square and then square root and stuff like that?
Absolutely. Here, this, of course, is what kind of function?
Quadratic. Polynomial.
It's a quadratic and therefore a polynomial, yes. Of highest power 2, that's true. Is it, which of these options have we got? One to one, many to one, or one to many?
So do you,
Although you mentioned quadratic in connection with this one, didn't you? Maybe I've changed. Maybe I've switched unhelpfully here, because you were discussing this, weren't you? Where 2 is mapping to 2 separate values. That's when you.
Yeah, I was imagining you get like an x squared equals 1, therefore x equals plus or minus 1 or something like that.
Yes, yes, no, that is the point. And maybe I shouldn't have gone here, which is, of course, I wonder if I was confused there, because I went here rather than here. Now, this is more like a square root graph.
Oh, okay, I didn't realise that. I thought it was like a log graph or something like that being translated.
Oh, yeah, could it be a log? It could equally well be a log having been translated. You're quite right.
Yeah.
But I think it's probably, it looks a bit more, to me, it looks a bit more like a parabola like that that's been rotated.
Yeah.
Now, so you're absolutely right, because if it was like that, now that is a graph of y values equal plus or minus root of x.
Yeah.
And you're absolutely right, the same thing is happening. A value of 2 here might be going to 1 or minus 1.
Yeah.
So exactly a case in point of what's happening here in the same way.
Yeah.
Okay, so this graph of y equals plus or minus root x is 1 to many in exactly the same way, yes. I absolutely agree. What about this, the inverse? Well, I shouldn't say inverse. We'll come to that in a second. But, well, you would expect me to call this the inverse of that. Y equals x squared. Maybe it's plus stuff. Oh, yes, and maybe this was plus stuff as well, wasn't it? That would affect the horizontal translation that we get there. And maybe this was plus 3 or something.
Okay.
So this was 1 to many, like that's 1 to many. What's this? The quadratic.
Well, one x value goes to one y value.
Yes, only 1. That's right.
Yeah. But one y value goes to 2x values, which.
Yes. So the point about this vocabulary here, all of those 3 options, 1 to 1, many to 1, 1 to many, they're all going from inputs which are usually x values.
Yeah.
There are exceptions, but the convention is that the horizontal axis is inputs. So it's always in this direction, from left to right in this diagram, from inputs to outputs. So the options are, is it 1 input to 1 output, many inputs to 1 output, or or do we get 1 input going to many outputs?
It's just 1 to 1 then, isn't it? I think.
Well, not this one.
Is it not? Oh.
Because there is more than 1 input going to the same output. Now did I say that wrong? Did I say going from? No, we're going from input. It's always inputs to outputs. Is it each single input having a single output? Is it potentially many inputs having a single output? Or is it one, or are there various single, or it might be 1 or more, that's confusing, but there might be 1, could we have 1 single input going to many outputs? Now you've excluded that for the right reason. You're saying it's not 1 to many like these 2 were.
Yeah.
But it's not 1 to 1 either, because you could have many inputs too anyway.
Oh yeah, because it's the same y value. Yeah, they're not negative. Yep. Okay, yep. So it's many to 1.
Yes. So the diagram for that one, if we were doing that kind of diagram, which they, you might find that in your book, is in that kind of diagram, what they're trying to illustrate is the fact that many inputs might be going to 1 output.
Yeah.
So the opposite situation to that. So this is, you can see how this is 1 to many, and this is many to 1.
Yeah.
Okay. What about this one?
That would just be 1 to 1.
Exactly.
Yeah.
The way you recognize a one-to-one function, you can probably see by now.
Just a straight line.
Straight, not necessarily straight.
Yeah.
I think this is one-to-one here.
Is it just when it doesn't loop back on itself?
Exactly. Horizontally or vertically. That's
Yeah.
exactly well put. Yes, if it goes back on itself either way, then it's not one-to-one. Okay.
Yeah.
This one, the cubic, probably a cubic, isn't it?
Yeah, I reckon so. 1 to many. No, wait. No, 1 to many could work, I think.
No, I don't think so. The way it's going, any one input is not going to many outputs.
Oh, wait, I've misread
input
it.
is only going to one output.
Yeah, I've put my axes on the wrong. It's one, no, many to.
Yeah, you have got many distinct inputs going to the same output.
Yeah.
So
Yeah.
notice it is kind of, in your words, going back on itself in the same direction that the quadratic is as well.
Yeah.
So it's many to one.
Yeah, okay.
I think this is the only example here. Oh, sorry, and it's not their example, is it? Interestingly, right. Yes, I changed this to a one to many.
Yeah.
In which case it becomes like example A. But their example F wasn't one to many, was it? So what was their example F before I've doctored it there?
It was just 1 to 1, wasn't it?
Just 1 to 1, and so it is like example B, although it's not a straight line. How could you describe what F has got in common with B? F before my change.
Well, it never loops back on itself.
Yes. Okay. What is it? There's jargon or technical vocabulary in maths for that. What we say is both of these are increasing.
Okay. Yeah.
Just like words in maths like similar. When you talk about similar shapes, you mean it in a stricter sense. A more powerful sense than normally. You don't mean just a bit similar. You mean absolutely similar. And it's the same here. This means absolutely always increasing and never changing its mind and going back and decreasing.
Yeah. Okay.
Whereas this one here is, no, bad example. This one here is increasing, then changing its mind and decreasing, and then increasing. So when you say a function or relation is increasing, you mean increasing all the way, which is what these two have in common.
Yeah, so they never loop back on themselves.
Again, yes, quite. Yeah. Well, that's what increasing means, but so also does, have we got an example here that's not increasing, but decreasing?
No, just decreasing.
I don't see an example here which is decreasing. But the point is, if they are increasing or decreasing, that means increasing all the way or decreasing all the way.
Yeah.
Then what of these three classifications have we got?
It would be 1 to 1.
It would be 1 to 1. So 1 to 1, if it's increasing, and it's just implied there that it's all the way, or decreasing all the way.
Yeah.
So if it's not increasing all the way or decreasing all the way, then it's got to be 1 to many or many to 1.
Yeah.
As I say, we don't talk about many to many because then, I mean, it's just ambiguous. You might mean 1 to 1 if you say many to many. If you say many inputs have got many distinct outputs. You might mean 1 to 1, or you might mean something more complicated. I'm guessing. I haven't worked it out, but let's not go there. It just doesn't happen. We don't say many to many.
Yeah. Okay. Yeah. Right.
Now, there is more. Increasing and decreasing, just like maxima and minima are both kinds of what? What are maxima and minima? Both.
Well, those are points where maximum, minimum points, like with differentiation and stuff.
That's right. So a local maximum or a local minimum are both kinds of what? Do we call them in general?
Points of inflection. No.
No.
No, that's where. No, that's where.
A point of inflection can be one of these things. In x cubed itself, it's horizontal at the origin. Oh, it's not one of these, of course, is it? Oh, that's interesting. Right. Yes, it's not just that both of these have another name, which applies to both of them, but this other thing that we call both of those could be neither of them as well. Oh God, I mean, that's confusing in itself. I could be clearer there, but this is that extra case where it's not a local maximum, it's not a local minimum.
Yeah.
But it is a case of what a local maximum and a local minimum both are examples of what. It's important because they do use this other word all the time as well. Instead of calling this a maximum, they might call it a what? Less specifically, in other words.
Well, it's a point where m equals 0.
Yes, yes.
Not.
But also a very common word for that is, well, what would it be, for example, if it was a distance time graph? Oh no, hang on. Yes, if it was a distance time graph, displacement against time. Then, so here you're moving away from the origin, and here you're moving back towards the origin. So you're moving, except at these points here, where you are
turning around.
And another word for not moving is?
Stationary. Oh, stationary points.
Exactly. Stationary points are the general, what maxima and minima are in general. They are both stationary points. And then, of course, I just realized here that my example here was neither of those, but it is a stationary point.
Yeah.
We would say that if we're moving towards, the x-axis, at the moment when we're on the x-axis, we're not actually moving.
Yeah, yeah, okay.
Vertically anyway. You might say we're moving horizontally, but just say the horizontal was time.
Yeah.
Only the vertical axis represented a spatial displacement. Then you're not actually moving at the origin there.
Yeah, okay.
Right.
So
now
stationary point literally means stationary.
Only for a distance time graph, yes.
Yeah.
In general, it's just used more loosely as the name of any point on a graph where the gradient is 0.
Yeah.
So it's kind of extended from its usual usage. It's metaphorical, really.
Yeah.
The word stationary. It just means a local maximum or minimum.
Yeah. Okay. Understand.
Or this inflection point, which is an inflection point, sorry.
Yeah.
Maxima and minima are not inflection points because they're coming down again, because they're still curved in a certain direction.
Yeah.
The inflection point in this example would be about here, wouldn't it?
Yeah.
Where you can see the steering wheel would be dead level and straight ahead at that point. But here the steering wheel is dead level straight ahead as the vehicle is turning right here, but from here onwards it's going to turn left.
Yeah.
So this is an inflection point, which is also a stationary point.
Yeah.
Anyway, that's all by the way, just because, just like maxima and minima are both stationary points, increasing and decreasing, which are both one-to-one, which we've mentioned. The other word I was going to mention, I'm thinking now I probably shouldn't, because I don't think it's you probably won't even find it in the book. I don't know. but this more posh mathematical word, monotonic, which may or may not
No, it doesn't.
appear in the index, just is a posh technical term meaning exactly either increasing or decreasing.
Okay, yeah.
Right, now we still haven't got to the bottom of this. I'm sorry. All right, we nearly have. I mean,
Yeah.
We've done part one. We've looked at everyone and see. Oh no, we haven't looked at E. Is that which one is that?
E. That's a reciprocal.
Yes, it is a reciprocal.
One to one.
One to one. Yes, it's
Yeah.
one to one because you're never getting more than one output from an input.
Yeah.
And all of the negatives are down here with that part of it, that part of the story, and all of the positives are up here, and they both look one to one in their own right, and
Yeah.
they don't interfere with each other. One to one, you're quite right. Yes, good. So B and E are one to one. Yes, let's do it that way. Which ones, which graphs, and let's assume that I haven't interfered here. Which of their examples are one to many?
A. C.
No, C is many to one, isn't it?
Oh, what? Yeah, many to one. Sorry.
You have to get it right. Yeah.
It's the wrong way round.
Yeah.
Yeah.
Well, it's exactly. I mean, they're exactly opposite to each other in a very important sense. Yeah, which we've just come to.
So many inputs to one output.
Yes. Which ones are many to one? Here.
Sorry, I've kind of got.
Well, it's always inputs to outputs. Yes. Sorry, you were starting to say. So many inputs to one output, which is this diagram here.
Yeah.
Many inputs X to one output Y would be which graphs?
That would be C, D, C and D.
Just C and D. Well done. Good.
Yeah.
One to many is which graphs?
It's just going to be A.
Yes. And one to one, and that just leaves one to one.
Being B, E, and F. Yeah.
Exactly. Good. Yes.
Yeah.
So that's all sorted out, and we can answer part B now, or part 2 of the question. Can the mapping represent, and when they say mapping, they mean in the sense of they're thinking of arrows. The thing about a mapping is you have two senses. You talk about a mapping from this. Oh, and what's the name of the set of inputs called?
That is the domain.
Good. And the set of outputs is called usually?
The range, yeah.
Yes. I mean, that's universal.
Yeah.
Sorry?
Because there's some questions in some tests and stuff I've done.
Yeah.
Where they give a function and they say state the domain for 2 marks and then state the range for 2 marks. Which sometimes I can do, sometimes I can't.
Yeah.
So it's easier when it's something like your function is log x and you know that you can't have a negative number or something like that. But
that's right. Yes. Well, always the way to do it is with a sketch.
Okay.
And when you've got your sketch, you're thinking in this way, which is also going to help. To answer that kind of question, what is the domain? Well, let's do that here. What's the domain for part A?
The domain.
I mean, let's say we have been told that point is 3 and that point is -3, and this point is I don't know, 2, and this point is -2. So what's the domain?
-3 to 3.
Yes, and the range?
Value -2 to 2.
That's right.
Yeah.
So here's the domain. here's the range, and then this question is about the mapping from the domain to the range. But then, as I say, it's ambiguous because it means from the whole of the domain to the whole of the range. And then it also means you might be talking about each individual mapping from a particular input to a particular output, or more than one particular output. You know, so it's the arrows. In one sense, mapping means the arrow, or you know, you're talking about the arrows in general, perhaps. In another sense, it means a correspondence between the whole domain and the whole range. So you've got those two senses zooming in and out.
Yeah. Okay.
What's the domain and range of part B? Graph B.
The values that can go in are from, well, X is any number.
Yes. You would probably clarify that as X is an element of what set of numbers
That
in this case?
is the weird Z, the phonic, no, that's integers.
Exactly. Z would be integers, and this would be R for?
Any real number, yeah.
Yes, that's right. Yeah. Any real number. And the range?
Would it's any real number again.
Yeah. The only difference is you would, to give the domain, you would say X is an element of the reals. To give the range, oh, did I say that right? To give the domain, you would say X is an element of the reals, and to give the range, you would say Y is an element of the reals. So that's how you distinguish in your answers by choosing X or Y, depending on domain or range. Well, what are the domain range of this quadratic here, which cuts the y-axis at 3, let us say?
The domain is X is any real number.
Good.
And the range is Y is greater than, in this case, 3.
Yes. Although Y is, it would be non-strict, wouldn't it? Oh, greater, not less, sorry. Greater than or?
Equal to
3.
Yeah.
Is how you would write the range.
Yeah.
This cubic here apparently reaches 3 and there and -3 there. But as I was writing that, I was thinking, yes, it's more complicated than that. Yeah, well, what do you think about the domain and range here for this cubic?
I mean,
I've put an interesting spanner in the works, which I could pretend was deliberate. But anyway.
Well, it could be the domain would be any value of X is any real number.
So that again.
Yeah. The range is Y any real number as well, because
yes. Yeah. So different situations here. The reason I perhaps got confused and put 3 and -3 there before realizing, oh, it's still going to be the same as it was here.
Yeah.
Although this is 1-to-1, whereas this is what?
Many to one.
Many to one. Yes. Good. So yes, and then you could think of this kind of diagram, or this kind it would be, because many inputs are leading to, in this part of the story, between 3 and -3, that's where you've got a many to one aspect. Whereas outside of that, did I say domain? Outside of that sub range.
Yeah.
But I could have said subdomain, meaning from whatever that X value is to that X value. So you have to be careful about domain and range, you know, and you can be careful to distinguish the two, and that's what these kinds of questions are about that you're alluding to, which will probably come to their examples too. What's the domain? So we've done domain and range there and here, and the here turned out to be part B. What are the domain and range for E?
X is any real number. I think, yeah.
Yeah, except for.
Oh, it's set for at the asymptote.
Yes, except for whatever that is there. Let's say that's 3.
Would
So
you just say x is not equal to 3 then? Or?
absolutely, yes. And
Yeah.
then it's obvious that you're saying also, apart from that, x is an element of the reals. So that would be a matter of taste how you put those together.
Yeah.
Whereas the ranges,
The range will be any value of y. Y is any real number.
any at all.
The asymptote doesn't affect it, does it?
Well, there is another asymptote.
Oh, the y. Oh, when so not at the bit very close to the x-axis.
Well, exactly, yes.
Yeah.
Y values of
X equals 0.
I think you mean
So y equals 0.
y. So y can't be 0, just like x can't be 3.
Yeah. Okay. Yeah, makes sense.
Yeah. And then we don't know whether we're talking about our version or their version of that. So maybe.
Yeah.
I ought to remove my addition there, though. Yes, that would be better, I think, because we do want to discuss this in a minute.
Yeah.
That's not the best way to do it. What's eraser? Oh damn! Hang on. What was it? Was it R? No, that's rectangle. Oh, I can't remember what eraser was. No, that's not right. Right. Okay. Sorry about this. So, yeah, good. Now and then.
Yeah.
Yes. So what do I want to do here? What shall I get rid of here?
The plus 2 and the plus or minus.
I think I'm happy with the +2 giving us a horizontal translation.
Okay.
But the plus or minus is no longer true. It's just which.
It's just plus.
Yes. So what we might do, although we often don't bother putting a plus to something that's positive, do we? But in the case of the quadratic, you probably do. Well, you might not actually. If you're given this in a question, they would just say x equals root of whatever.
Yeah.
But you would notice that it was the plus version of the square root. And you think, oh, that's relevant. As we're going to see in a second. We're finally going to get to the point of this question, part 2. I think.
Yeah.
Yeah. Oh, yes. But what are the domain and range of part F?
Domain would be x is greater than whatever the point is but by the origin, near the origin.
Good. So the domain is greater than -2 or whatever, yeah?
Yeah.
And
the range is y is greater than greater than 0, but less than the asymptote.
Well, if it's possibly, depending on what kind of curve it is, it might have an asymptote. But if it's a parabola, it won't have, will it?
Yeah.
Notice a parabola is never reaching a limit x-wise horizontally, is it?
No. Yeah.
So if this is a parabola, then no, there's no. The only restriction on the range is what?
Greater than 0.
Yes. Or greater than or equal to 0, depending on whether it's strict or non-strict, which is not necessarily clear from this graph.
Yeah. Yeah.
Right. Now, finally, part two. Could the mapping, which has two senses, sort of zoomed in and out, represent a function? Do you want to take a guess? Perhaps you are vaguely aware of when
Does that mean? Does that
which of
basically
these are function? Sorry? Oh,
Does that basically mean can I write an equation to make this graph?
no, because we, well, to give the game away, or it's not a game, well, anyway, to, this has got an equation, but it's not a, when I did this,
Yeah.
it's got an equation, but it's not a
Uh,
function,
no, oh, oh, okay.
which might be surprising. You know, it looks as respectable as all the others, but it's not a function, whereas this is a function. By taking just the positive outputs for X inputs, we've made sure that we are either one-to-one, as we do seem to be one-to-one,
Yeah.
but it would still be a function, because you would be surprised if this one, where y is probably equal to x cubed minus 3x or something, you would be surprised if that wasn't a function, wouldn't you?
Yeah.
So it would be surprising if we didn't call, now what kind was this? One-to-one, many-to-one, or one-to-many?
This was many to one.
Yes. So that kind of cubic is many-to-one. We noticed in passing, didn't we, that the original cubic y equals x cubed, pure and simple. What kind is that?
That is 1-to-1.
That's one-to-one. Good.
Yeah.
Cubics in general are many-to-one, but yes, we're used to calling them functions, aren't we?
Yeah. Yeah.
So what do we call it when it's not a function? This one here, it's perfectly good. We can draw a graph of it and we can represent it by an equation, but it'll have a minus there as well. So it's y. We have to prevaricate and say, well, y isn't, we can't use the definite article here. We can't say the output is this function of x.
Yeah.
The output might be this or that.
Yeah.
You know, result of doing the stuff to the input. But we can, what we call this instead is a relation.
Okay. Yeah.
So, but it's not a function. And why does it matter? I mean, I always get a bit hazy on that. I think I have a feeling there are reasons it matters that I don't fully grasp, as well as the one I'm aware of, which I'll share with you. But the difference, the big difference. Oh no, sorry, no, that's a slightly different question. Yes, why do we care about whether something is a function or not? Oh, and by the way, let's agree which ones are functions here.
The B, C, D, and E are all functions.
Yes, exactly.
Yeah.
Not A and F, because they are both.
They're both. Is it that plus and minus things?
It's to do with that, yes.
Yeah.
What difference does that? I mean, how did we classify A and F?
Well, A was many to one to many.
Yes.
So being one to many means you can't be a function.
Yes, that's exactly it.
I didn't know that.
Probably it took a while to get there, but but if it's if it's one to many, it can't be a function. Now you're saying, why do we care about that? Privileging the ones which are either one to one or many to one.
Yeah.
And then I said, well, one basic reason, and then I had to change my mind. No, what I'm going to say, no, for this reason I was thinking of, you have to be a one-to-one.
Yeah.
And that's what this question is about. State whether the mapping could, oh no, it's not, sorry. Their question is whether it could represent a function. And then,
Yeah.
so the straight answer to their question is, which ones can represent a function again?
B, C, D, E.
Yeah, because
Yeah.
they're
not many to one. No, they're not one to many.
they're not one to many. Some of them are many to one,
Yeah.
but they're not one to many. Right. Now, why do we bother privileging all of the rest as functions to the exclusion of those? And that's no, I have to remain hazy on that, because I was going to offer that the reason is, but that would be wrong for all of them. But what's special about one-to-one functions is, and this is important for all of these questions, what's special about one-to-one functions is you can do what we failed to do with this perfectly good function, which is a quadratic. Yeah. It's a function because it's not one-to-many, right?
Yeah.
But look what we were unable to do. Have an inverse function.
Okay.
The inverse of that turned out to be a relation, sure, but not a function because it's one-to-many.
Okay, yeah.
So to have an inverse, for a function to have an inverse which is a function, is what we mean by having an inverse, really.
Yeah.
It has to be what? What does a function have to be in order to have an inverse?
One-to-one.
It has to be one-to-one, either increasing always or decreasing always.
Yeah.
Monotonic, going to be Flash. Yeah. Was I going to say something else? No, that's got to do now, hasn't it? We could go on to question this other question. Yes. All right. That wasn't an exam question either. Right. So yes. Oh, I was wondering if that did answer what I was vague about. I mean, yeah, if you're not one-to-one, then
yeah.
Well, anyway, you can't find the inverse relation, perhaps, because you would have to. I don't know. No, let's leave that. Right, fine. So back to here and different kinds of things. What about number 6? That is the algebraic way of doing, like last week, that slightly kind of car crash situation where we tried squaring both sides and shouldn't have done, and we did it as a graph.
Yeah.
Well, I'm just saying we should have done it as a graph.
Yeah.
Drawing that as a graph is the clear and preferable way of doing this kind of algebra, where you tell the algebra story of f of x for 2 separate parts of the x-axis, like that.
Okay, yeah.
So when they say sketch the graph here, you know, it's preferable anyway. As soon as you see f of x equals curly braces and then 2 different stories for different sections of the x-axis,
yeah,
you want to sketch it mentally at least, and,
okay,
and probably attack the problem using the graph. If you've sketched a half-decent graph, chances are you crack the problem. Should we do this one? Do you want to do number 6?
Yeah, I'll give it a go.
Yeah.
Yeah.
I'm not sure how relevant it is to what you meant by functions, but well, it probably is. Yeah. Let's do that. So let's sketch the graph.
So f of x.
Can I do this relatively quickly? Type stroke oh, it's a bit thick. I'll go with that for now. Now what? Oh, yes. And then all I'm trying to do is draw some axes here. Sorry, it's taking an age. And this time I'll get a more sensible. No, I'll leave that one thick, otherwise it'll look weird. Right. So sketch the graph of, between these values here, from -2 to 6.
Yeah.
Interesting, because we're still left with, so if that's -2 and that's 6, it's still changing its story at x equals 1.
Yeah.
So have you drawn it?
No, I haven't seen this type of question before. This feels odd because
Right.
I don't remember seeing.
Maybe they're not going to inflict this particular delight on you in MEI, I think it is you're doing, or we're not sure if it's MEI.
I'm OCR. No.
If at any point, I wonder where I picked up the idea that, where are you? I can easily find out. Not that it matters all that much because I haven't got your materials anyway, but where are you? Which school is it again that you're at?
I'm at Monk's Walk.
Monk's Walk in Welling, isn't it? So
yeah.
So I could easily find out whether you're MEI or not. Anyway, maybe this isn't on your syllabus, but you can see all it's doing is giving you a non-graphic version of the graph. It's saying for x values less than 1, and because they've said we've got to be greater than -2, it'll be for this section of the x-axis.
Yeah.
We've just got a straight line with a gradient of -1 going to the origin.
Okay.
In other words, yes, these are y values. Y equals -x, and this is y equals x -2.
It's essentially asking me to draw two graphs.
Yes, absolutely. And hopefully, I mean, I say hopefully, it might not be the case, but you'll often find in their examples that it'll be the case that they do join together.
Yeah. So okay. So the first bit's just going to be a straight line towards the origin.
Yes, it's going to go through the origin, isn't it? Okay.
Going through the origin to 1.
Yeah. So hopefully a gradient plausibly like 1. Yeah, good. And then now I must make that a bit thinner now.
And then x -2.
And then since the gradient is 1. Sorry, yes, you were going to say.
It's going to go through -2 on the y-axis.
Yeah.
With the same gradient.
Yeah. So because it's only starting there, but as you say, it's got the same gradient. I think it's at right angles, isn't it?
Yeah.
Those are perpendicular gradients, aren't they? 1 and -1.
Yeah. Yeah.
Great.
I think.
So we've, but it would, that's a point. Whew. We want to go right up to here, don't we?
Yeah, all the way to...
You probably did, sorry, I neglected to extend it far enough there. So like that, so that it's just directly over the 6.
Yeah.
Great.
Okay.
And then find the values of x for which the function, it bears a passing resemblance, doesn't it, to the modulus graphs? But unlike the modulus graphs, it's got...
it's gone below the
yes
axes.
Absolutely.
I think the mod graphs look quite cool because all the sharp corners.
Well, quite, yes, which might be called a discontinuity. Even though they're touching, is that a discontinuity? Yes, because you can't differentiate at that point there.
Okay.
It wouldn't make sense to talk about the gradient at that point. X1. Although it might, because, so I take it, perhaps I have, yes, then you have to distinguish between, no, well, okay, I'd need to revise that, whether it's continuous or not at that point.
Yeah.
Yes, I need to look that. I should be able to answer it, but I can't. Right. So anyway, that's the situation. But what about part B? Find the values of x for which f of x is equal to -1/2.
So do we just take the two lines and set them to -1/2? Or,
yes, by doing what? What does that really mean graphically?
a line at y equals -1/2.
Yes. What kind of line is that?
Straight line, horizontal.
Horizontal. Yeah, absolutely. So basically, you would draw that. Would be the best way to do it. And indeed, you probably won't even have to do the algebra then. You can just see that the x values are what and what.
-0.5-ish.
The x values.
Oh wait, no, that's the y value. Positive 0.5-ish.
Yeah.
And 1.35, 1.3-ish.
Well, on mine, yeah, probably. But I think that's meant to be 2, isn't it? Didn't we agree? Because that was a gradient of 1 going through 2 there as well. So we can probably see that they are precisely 1/2 and 1.5.
Yeah.
But to check that, the graph basically tells you which equations to solve. So this would give us 2 equations, which the graph tells you
x equals so that would be x equals 1/2 and x equals 1.5. Yeah.
Yeah. I think I see what you mean. Yeah.
Yeah, I'm just saying -x equals -1/2
and then also x
minus 2 equals -1/2.
X minus 2 equals -1/2. And because both of those are not going to give you more than one, you want both of the only solutions to those. So that's all there is to it. But that's true also with the modulus graphs. By sketching it, you see how answering that kind of question breaks into 2 separate questions.
Yeah.
And sketching it solves it. And then the next one was another exam question. Hopefully a bit different with the domains and ranges, maybe, I'm thinking. Now this notation here is rather unusual. And it might not be on your syllabus at all, but it's not really on this syllabus much.
I have seen it. It's just, doesn't it just mean P of X?
Yes, equals that stuff. What they're trying to do is allude to this kind of diagram, because the little arrow there means that, and it would have to be many to one, otherwise it's not a function. So it can't be this kind of diagram. So the point is, because it's a function, they're able to use that notation to say, to specify the arithmetic that gets you from any input to the other end of the arrow. So the arrow is meant to be taken literally there. It's taking any input to the result of that arithmetic.
Okay, yeah, it's done.
So yeah, in the end, you're quite right. It just means that, hang on. It just means that the P function of X equals that stuff.
Yeah.
Quite right. Now, what's the domain and range of P?
Domain.
Oh, well, one of those questions is fairer than the other.
Yeah.
The domain is what?
The domain of P is X is any real number. It says that.
Yes, and it says that. That's right. The domain is what they usually give you as an afterthought, which you get used to half ignoring.
Yeah.
Which is sort of half okay. And they're just covering their own backs, really, from a complaint. You know, because you might say, well, this can't happen for all values of X, so they might exclude one or two. And then they just say it as an unnecessary afterthought as well.
Yeah.
In this case, but it does confirm that the domain probably, well, actually, they're confirming that the domain is all of the reals, yes. To find the range, we would have to think about the graph and ask what about the graph of that?
What the minimum point is.
Yes. So it's a parabola, and we just want the minimum point. What's a good way to find the minimum point of a quadratic?
Completing the square.
Exactly. Good. And then we'd know for sure.
Yeah.
And what are the domain and range for Q?
Well, domain is given as any real number. The range would be any real number.
Yes, fine. Straight line graph, isn't it? So, and it's also what kind of function?
1-to-1.
Whereas the quadratic is
many to one.
Yes, it's.
Yeah.
I mean, you've totally got to grips with it, but it's worth asking about that quite a lot at this stage to get completely on top of it. Good. Right. So which of P and Q have an inverse function?
Which of them has it? Q.
Q has an inverse because it's a straight increasing function. But not P because it's
many to one.
Yes, and not 1-to-1. That, yes. Right, P Q of X. You know that you could write that as P. How would you read it, by the way? Probably better than. Yeah.
I would just say PQ of X. I think
it's better to say P of Q of X.
Okay.
Although actually it's a bit pedantic. but it's useful to be saying to yourself, of course I could write that like that, couldn't I?
Yeah.
So you would know how to do that?
I think just put 2x plus 1 into all the x values of
exactly
P. So 2x plus 1 all squared plus 3 times 2x plus 1 minus 4.
Exactly that. And then it would be a simple matter of expanding and simplifying and stuff, wouldn't it? What am I doing? Oh yeah, that. 3 times 2x plus 1.
Yeah.
Minus, 4. And just simplify, yes. And then if you solve that one being equal to Q of X, what's Q of X?
Would be 2 times 2x plus 1 plus 1.
Yeah. Good. So just putting that equal to that is just really simple algebra.
Solving.
Yeah. But this number, let's do number 8. That's more interesting, I think. In fact, you see that we haven't really covered all that much, I'm afraid. But I'm sure we have done the most important stuff. The stuff we haven't done will make more sense now, I hope. Right, number 8. The function g is defined as 2x plus 7, but the domain is restricting it just to what part of the grid?
Any number greater than or equal to 0 for x.
For x, so that means that we've got anything kind of east of the y-axis.
No, they don't go into that, do they?
Well, I was just trying to agree with you, though. Are you not saying that this graph is only happening over here.
Yes.
Because if you look at the graph of
Yeah.
2x plus 7, it kind of looks like that.
Goes all-
doesn't it?
Yeah.
So this restriction of the domain is removing that bit.
Yeah. Is rubbing it out essentially,
Yes,
so to speak. Yeah.
but that's what you meant.
Yeah. Yeah. That's what.
Fine.
Only on the
That's also what I
positive.
meant by east of. Am I getting my west and east mixed up?
Yeah.
Do something?
No, I don't get east and west right. I get north and south fine, but east and west.
It is east, isn't it? WE for we. Yeah. It is east of
yeah.
the y-axis. Or I could have said to the right of the y-axis. That might have been. Right. So sketch it. Well, we have now, haven't we? And find the range.
Yeah.
And the range is what?
Y is greater than 7. Or greater than or equal to 7.
Yes. Good. Yes. Because of that non-strict aspect.
Yeah.
Yes, quite. So 7 is the y-intercept included. Now here, find y equals, you would read that as?
The inverse function of g.
Yeah.
X.
So how do you do that? Do you know the trick?
I've done it before, but it's kind of gone rusty and I can't quite remember. I tried it the other day and I got the answer horribly wrong.
All right. Well, starting with y equals the g stuff.
Yeah.
So if you go y equals 2x plus 7, and then say, okay, well, we want to go, because that arrow doesn't really belong there, does it really? I mean, I mean, g, inverse g of x is not that at all. This is, we could clarify that as that's g of x.
Yeah.
But then if we want, I don't know about an equal sign here, but if we want to think about reverse g of x, then we are basically reversing x and y, aren't we? So we ought to be able to write that, and that's the trick. If you get that right,
Yeah.
if you know to do that, then no matter how bad the algebra, you know that you're trying to make y the subject.
Okay, make y the subject.
Yeah.
So
flip them round. By the way,
yeah.
yes, we did talk briefly about whether these are going to have an inverse or not, didn't we?
Briefly, yeah.
Which ones are going to have an inverse function?
1 to 1.
The 1-to-1 ones, yes. So now, what will they look like? What will the graphs of the inverse look like? Oh, shameful omission here. Yes, what do the graphs of an inverse look like?
Are they reflection in an axis or something?
Absolutely, or not an axis, actually.
Are they a reflection in y equals x?
Exactly, precisely because that's what's happening. We're flipping x and y.
Yeah.
So if for any point on the graph you say, well, I'm going to exchange the x and y coordinates.
Yeah.
What you're effectively doing then is reflecting in that line there.
Okay. Yeah.
Which you might say, well, I could do that with any of these relations. What if it is one to many? I could still reflect that in here. Oh, I don't know. How would that be? Something like that? I don't know.
Yeah.
But yeah, you could have a reflection in that. You just wouldn't want to call the reflection a function anymore, even if this one was. And this one wasn't even a function already. This one is a function, the quadratic.
Yeah.
But you would say, okay, when I reflect it, I get a perfectly nice graph here. Could improve on that slightly, maybe. But this isn't a function because it's not like that. It's one to many.
Yeah.
So your quadratic there does not have an inverse.
Okay. Yeah.
Even though it reflects, and reflecting in the line y equals x is how you find an inverse. So it's how you draw the inverse if there is an inverse function. And you might have other reasons to reflect it. You might even call one an inverse of the other, but probably not. We do reserve the word inverse for functions. And functions only have inverses if their inverse is a function.
Okay.
So, you know, you restrict inverse to functions basically.
Yeah.
Even though you could do the reflection with anything.
Okay, yeah, that makes sense. I get that.
So sketch the inverse on the same axes, stating the relationship between the two graphs would just be a matter of
reflecting it in y equals x.
Now, because I did my my very rough and ready graph, wasn't it? I mean, it was hardly a straight line, let alone having a constant gradient of 2. But if it was a constant gradient of 2, then you would find that kind of. So it wasn't like this one up here where they might have been. I don't know whether they were the same gradient. Anyway, same thing here really. So yes, you just get used to. You know, that's an easy 2 marks because you know the. Oh yes, I'm just reflecting in the line.
Y equals x. Yeah.
Because that's always what's happening graphically with an inverse.
Yeah.
Okay. Now, I'm slightly over, not much, because we didn't start till 10:02. What was I going to say? Yes, let's just look at this very next one, because there probably is a lot of stuff I haven't. Yes, this is what you mentioned. Well, it's not quite. What we haven't done much of is composition of graphs. 7 was a bit composition-y, but they didn't ask us about the domain and range of the composites, which they might have done in number 7. This is about inverse and domain and range, but not necessarily composites. So still not brilliant, but let's just do that.
Yeah. Okay. Sorry. The function f is defined by x mapping to, or f of x equals that fraction. Yeah.
For this domain, x value is strictly larger than 1.
Yeah. Okay.
So if we were to draw it, we've no idea. Okay, it's a relatively hard one to draw because it's what kind?
It is. Is it no, it's not.
Yeah, it's got a reciprocal element.
Yeah.
I mean, we could simplify it. We could take out. I mean, I would be inclined to think of it as 2x minus 2 plus 5 over x minus 1. Do you see why?
I see why it's still correct, but I don't know why we do it that way.
Because then I can see that it's 2 plus 5 over x minus 1. So now I can see better how it translates and scales from an original reciprocal graph.
Okay, yeah.
I can see I've got a horizontal translation by 1, a vertical scaling by 5, and then a vertical translation of 2.
Okay, where did the x on the top go?
Because that much of the fraction was just 2.
Okay, yeah.
Because 2x minus 2 is double x minus 1.
Yeah. Yeah, okay.
So it's just breaking into 2 pieces, 2 plus that.
Okay, understand, yeah.
So yes, you know, you've basically got that scaled a bit and translated 2 ways. So we have sketched it fairly quickly, or have we? Oh yeah, yes, it is rather. It is. I thought it was going to have a slanted asymptote, but not. No, it's not. No, it's just two translations from that. So the asymptotes are in different places. One to the right.
Yeah.
And two up. And you can imagine the rest. Otherwise, it'll.
Yeah.
But most of it will be down here, won't it? And the rest up there.
Yeah. I think that. Yeah, that makes sense.
Anyway, you didn't have to think about the graph in this case, because they're saying find the inverse of a function. They've said it's a function. They haven't said it's 1-to-1. But if they've invited us to find the inverse, it must be 1-to-1.
Yeah.
Oh, by the way, this function is only east of this vertical line x equals 1, isn't it? So they have scratched out all of that.
Yeah. Okay, yeah.
So we've just got this top right corner.
Yeah.
As it happens. Not that we needed to draw the graph necessarily, but it never hurts.
Yeah.
Now, using the algebraic approach here, tell me what to write for A, finding the inverse.
So y equals 2x.
Might as well start with that version, because if for no other reason that they haven't bothered saying y equals.
Yeah.
And you need a y. You can't do this very easily with f of x. Some people do, but I would use a y so that now you can say what?
Do you want to times by x?
No, we're finding the inverse.
Yeah.
So graphically, finding the inverse is like reflecting in the line y equals x, because it's like just flipping x and y.
Can you just put x into y and y into x?
Absolutely.
Oh.
We're saying, if this is f, roughly speaking,
yeah,
this is reverse f, because we've.
Oh, I thought you actually had to mathematically rearrange it.
Oh, in a minute, we want to mathematically rearrange this version, but you've got to do that step first.
Oh, okay.
Because after all, y is already the subject here in the original version.
Yeah.
It's only by flipping them that we have a task to make y the subject again.
Oh, okay. Yeah. Okay. So which equals 2y plus 3. And then we make y the subject.
Yes. Yes. Which is not a trivial example. So tell me what to do.
Times by y minus 1.
Yes, good. So x times y minus 1 equals.
Divide by 2y plus 3 and divide by.
Let's go step by step.
Yeah.
You did say multiply both sides by y minus 1. So I've done that there, right?
Yeah.
What's next?
I think divide by 2y plus 3.
I don't get that, because then we're more or less back here, aren't we? We've taken the reciprocal of each side or something.
So we need to make, oh wait, it's y the subject, not x the subject. Oh, expand the bracket. X, y minus x.
Yes.
Yeah.
Equals 2y plus 3. And then?
Plus x minus 2y.
From each side, absolutely, yes. So we've got xy minus 2y.
And then factorize out.
Yes, good. You've seen.
Y. Yeah.
That's the tricky bit that you saw it. Well done.
So therefore, y is equal to 3 plus x over x minus 2.
Exactly. Good.
or x plus 3. And
or whichever. Yeah. Right. Okay. Now state the range of the inverse. Well, it's a trick question in a way. Do you see why?
No. No.
Well, partly because it's a reflection, but also because by reflecting,
Yeah.
we're doing the opposite mapping that we've got here. From x to y, now we're going from what we were calling y, but we're now calling x, back to the original set. So we really are literally just reversing the mapping. So the old domain is going to be the new
range.
And
Okay.
it really is that simple with inverses.
Oh, okay. So the range will be the original domain, which is x is any real number that's greater than 1.
Yes, except that they're going to look at that, maybe grudge you the mark for that if you don't say what version instead. Because it's a range now, not a domain.
Range is
It's the same set of numbers.
Y of any real number.
Yes.
Yeah.
Yes. I mean, it's still the same set of values, but
yeah.
now we're calling it Y, aren't we, instead of X?
Yeah. Yeah.
So
okay.
So they just flip. You just have to be careful how you say it.
Yeah. Okay. That makes sense.
And by the way, by thinking about the graph, we did state the range of F, didn't we? They didn't ask us to, but we can say the range of F was, oh gosh. Where did the scaling come in? It was as a sequence of 3 transformations. It might matter which the order they came in, mightn't it?
Yeah.
So if we go from just 1 over x, I think we have to end up doing this last. So
yeah.
Yeah, it can be tricky deciding whether it makes any difference whether the scaling comes before a translation, and it can make an awful difference. And that is relevant to this topic, where composites, by the way, I didn't draw any of this kind of diagram, which is always great. So I wonder why I didn't need this. So PQ meant not that way, was it? It was Q followed by P, as you quite rightly made explicit.
Yeah.
So here you would have, so the whole thing, you would say that was P of Q. But it's kind of the other way around. You're aware of that. Anyway, I'm just mentioning that kind of diagram because it could help in this conundrum.
Yeah. Okay. Yeah. Anyway. Yeah, I guess.
Leave it for now, anyway.